Hello everyone, welcome to this video presentation. My name is Aljoscha Pollmann. I'm working at the Fraunhofer ISI in Karlsruhe, Germany, and I would like to give you a short presentation on our study. Waste heat as a driver for greenfield heat networks, planning trade-offs illustrated using a case study for Zelzate, Belgium. First, I will give you a brief overview over the research area, the methods used, and finally I'm going to present the results of our investigation, namely the planning trade-offs that occurred. Who are we? This research was conducted as part of the onHeat project, which is an EU Horizon 2020 funded project that offers municipalities support to start, continue or improve their strategic heating and cooling planning. One of the municipalities that applied for our support facility is Zelzate in Belgium. So to start off, a quick overview over the research area. Zelzate is a city of around 13,000 inhabitants located north of Ghent in the province of East Flanders. South of the city center is the location of an ArcelorMittal steel mill. The local authorities approached the onHeat team with an inquiry to investigate the use of excess heat from this steel plant. The local government has put special interest in the supply of a psychiatric center located close to the steel mill, as well as several public buildings throughout the center of Zelzate. Additionally, the government wanted to investigate the possibilities of adding other main demanders within the city center of Zelzate to the network. You can see the location of these demand points in the map. According to these variables, some key planning questions arose. For example, should the main objective be the full utilization of the available waste heat? Or should the main goal be a maximal net present value? Or should the main objective be to connect the most buildings as possible? These different approaches led to further planning steps, namely the development of different technical scenarios of the extent of the network to be built, as well as the definition of indicators to compare the technical scenarios and their performance. To simulate and optimize the technical scenarios that I'm about to present, the open source heat planning tool Thermos was used. The first step was then to prepare the provided datasets to utilize it in the software. So the municipality provided demand data on a neighborhood scale. Since Thermos is calculating a network based on address level demand data, the raw data had to be processed using GIS software. As you can see in the table in column 2, Thermos has different estimation models that provide different levels of estimation accuracy. For further info on that topic, please refer to the Thermos homepage. However, as the table shows in column 4, the estimation accuracy could be enhanced to more than 99% of the reference demand for the whole research area. Further investigations on individual buildings where the demand data was known have revealed that the estimation accuracy is also very precise on single buildings when the data set is prepared in a proper way. On the basis of the now accurate base data, 3 technical scenarios have been investigated. The first one being the main demander scenario. Here only the main demanders are as previously shown in the map are part of the heat network. The second scenario would be the line densification approach. Here the main demanders are as well connected. Additionally, the buildings that are along the connecting pipes between these main demanders are also connected. And lastly, the full extent approach. Again, all main demanders are part of the network, but additionally, all buildings within the center of Zelzate are also part of the network. To compare the strength and weaknesses of the different scenarios, I've just presented, a set of indicators has been defined. These indicators are divided into three categories: energy costs, efficiency, and environmental impact. The first indicator is the total heat distribution costs, so the annualized costs to distribute waste heat considering the infrastructure and the operational costs. The second indicator is the demand covered by the district heating network. So it represents the share of heat demand of Zelzate covered by the district heating network. The third indicator being the share of excess heat within this district heating network. The fourth indicator are the heat losses, so the ratio between energy delivered at the heat exchanger and the amount of energy received at the buildings. And lastly, the fifth indicator being the amount of avoided emissions compared to the current emissions of today's heat supply mix. After running the simulations through Thermos, the following results could be observed. If you would like to take a closer look at this table, I would suggest to pause the video now and have a look. But briefly said, while the main demanders approach and the full extent approach are kind of the counterparts to each other, performing best in the areas the other approaches worst and vice versa, the line densification approach seems to combine the strength of the other approaches. The line densification approach is never the worst performing approach when considering the indicators. However, all approaches have their specific strength and weaknesses, which ultimately lead to planning trade-offs. These trade-offs being of different magnitude. The main demanders approach, for example, has the advantage of being the cheapest, requiring the least amount of construction and also benefits on the operational side. These benefits come at the trade-off that this network would have a limited impact on the reduction targets the municipality wants to achieve. It would also be inaccessible for any homeowner that wants to be connected to the network. And lastly, this approach bears the risk of lock-in effects, meaning once the pipework is in the ground, it can't be changed easily. If future extensions would require larger pipes. The line densification approach has the same advantages as the main demanders approach, but the additional benefit that only a little more effort in construction has the benefit of connecting more buildings. But as well, there are some trade-offs. Still, we would have lock-in effects and the system is not accessible for anyone not residing along the connecting pipes. And lastly, the full extent approach has its own advantages. For example, the elimination of lock-in effects and a high contribution to achieve the reduction targets when supplied with the renewable energies. But it comes at the trade-offs of requiring huge construction works, large capital costs, and comparably weak performance in terms of operational costs and heat losses. So in conclusion, all technical solutions have their specific technical advantages and disadvantages. However, the local circumstances, actors' goals and commitments determine the acceptance of certain trade-offs. So the trade-offs for the community are, for example, if you aim for a high district heating share, you are going to have high capital and distribution costs for the district heating operator. But houses only connect if the central district heating price is cheaper than decentral heating, meaning the district heating operator needs low-cost heat generation. If the DH operator has the perception that the solution is not feasible, he tends to choose a smaller network. So if you go for the low DH share, then you would have the benefit of low capital and distribution costs for the DH operator. In the case of Zelzate, the excess heat is very cheap. So this arrangement seems to be a safe business case for the DH operator. However, the rest of Zelzate buildings still has to decarbonize to meet the reduction targets. This means that homeowners have to renovate and invest in new technologies, for example heat pumps. However, the cost for those projects are also underlying market uncertainties. For example, renovation costs might increase, so the homeowner's perceived risk would determine if he wants to connect to the network or renovate his house. So if he perceives high risk, he would like to connect to the district heating network, and if he perceives low market risk and thinks decarbonizing his home on his own is cheaper, he would not connect to the district heating network. But in case of a small district heating network share, homeowners would be excluded from a connection. So to conclude this aspect, the overall market perception of all actors, meaning district heating operators and homeowners, determines the individual decisions in development and planning. The market uncertainties and the assessment of the markets determine the planning and decision making of the DH operator as well as other market participants. This gets especially important in view of uncertain data and external circumstances, for example, inflation, energy prices, or political agendas that might change. And lastly, the limitations of our approach. Our approach is only focused on the mentioned indicators. A more universal approach could lead to different conclusions and reveal other opportunities. The pure economic assessment is limited, and technical assessments should be combined with market surveys to identify local uncertainties and needs in advance. So thank you for your attention. Wishing you a great day. Bye.